Hello, and welcome to your Week 3 lecture, which is again a video, just in an effort to get us caught up. I'm going to do it this way, and then next week we should be kind of on track and we'll be good to go this Friday. So, we're working on Chapter 3, we're looking at Chapter 3, or Module 3, as Cisco calls it now, Protocols and Models. So this is everything we're going to look at today. So protocols are just rules, right? And the fundamentals on how they work has to be standard because networks can vary in size and complexity. So it's not just enough to have a connection. You have to have some kind of agreement on how devices communicate. And it's based off of the communication model for people, because that's what we did. We based things off of, when we created computers, things in the natural world around us, and made them work that way, because it's logical. So there's three elements to the communication. There's a source, the sender, a destination, the receiver, and some kind of channel that provides the path for your communications. That's the media, right? With me so far, hopefully. Can't really ask that, but usually I do. It's hard with a video. Now, all communications are governed by protocols, and they're simply the rules that communications will follow. And these rules vary depending on the protocol we're using. So in a conversation between two people, we've got a message, a transmitter, some sort of medium. It could be verbal, it could be written, it could be sign language, right? It could be nonverbal communication as well. There's all kinds of that. Things like your tone and your mannerisms. And a receiver. That's the destination. Now, in computing terms, we've got two devices connected over a network. One is the source, one is the destination. It's transmitted over a medium, it's received by the other, and it's put back together. Same kind of idea. Now, individuals have to use established rules or agreements that govern how the conversation is going to go. There's two copies of the same message down here. But the first one is difficult to read because it's not formatted properly. The second one is formatted properly. So in that first one, there's punctuation's funky, capitalization's funny, spacing's not right, and they even switch languages in the middle. Second one is a lot more sensible. When we're dealing with computing, sorry, something funny going on in my throat right now. I'm not sick, just allergies. Computing communication works exactly the same as we're going to see. Now, protocols, all protocols, whether they're computing or not, have to account for all of the following: an identified source and destination, or sender and receiver, a common language and grammar, your speeding and timing of delivery. For example, if I pause for a minute or two in the middle of a sentence, you don't know what's going on, right? And some kind of confirmation or acknowledgement requirements, if at all. It's, again, normally I'd be giving this lecture in person or online in the virtual classroom. If we're in person, I can look around the room and I can tell if people are paying attention, or that guy's sleeping in the corner, that sort of thing. That's still some kind of acknowledgement. Now, we're dealing with computers, of course, so can't quite deal with that exact thing. And on top of that, computer networking protocols have to agree on the message encoding. And we're going to look at what all of these mean shortly. The formatting and encapsulation, the size, the timing, and your delivery options. Makes sense so far, hopefully. So the encoding is simply the process of converting the information into another acceptable form for transmission. And then it's sent out over the medium, and at the other end it's decoded, so the reverse is done, and it's put back together into the original information. Your formatting and encapsulation, that's just simply the structure that it uses when it's sent out. Message formats depend on the type of message and the channel that it's being used to deliver the message. So we've got on the left here, we've got an example of a letter in an envelope, which you may not, well, nobody uses those anymore, right? But it's still a good example. And you can think of that envelope in networking terms as, well, it's a packet, right? And here's a packet header. So we've got our source and destination IP address, our version, and a whole bunch of other fields that we're going to look at in a little while. Now when it comes to the size, both hosts have to agree on what an appropriate size is for the medium that's being used, because messages are sent out over the network in some representation of binary, ones and zeros. So first they're broken down into bits. Those bits are then encoded into either a pattern of light or sound or electrical impulses. And the host must, on the other end, the destination, must decode that and put it back together to interpret the message. It's pretty crazy when you think about it. The timing includes a whole bunch of things. The flow control, so that's what manages the date of transmission and defines how much information can be sent, when it can be sent, when it can be delivered, and the speed, all that stuff. The response timeout, so that's how long devices wait before they consider the communication done for a reply. And then the access method. So this determines when somebody, that's the who, can send a message. So there could be a bunch of rules governing things like collisions, which is what happens when more than one device tries to communicate at the same time and the messages become corrupt. Some protocols try to prevent these, others try to recover after they happen. We're going to look at those again. I know I'm saying that a lot, but this is building to something, right? As far as your delivery options for network communication, it could be unicast, so that's one-to-one communication. It could be multicast, so that's one-to-many, but not necessarily to everybody. Or it could be broadcast, and that's one to everybody else except themselves. Now, broadcasts are used in IPv4, but in IPv6 they're not. We use Anycast for IPv6, which kind of does the same thing, but it also kind of does it differently, so it's not a broadcast. It's one of the improvements that IPv6 added over IPv4, and we're going to look at that more in depth in a later lecture. Now, when you're looking at documentation, you could see any of these following sort of diagrams for your different types of options. This will appear in the Cisco textbook. Normally I would ask if you're with me so far. That makes sense. Hopefully you are. So networking equipment, network protocols define common rules. They could be implemented in software or hardware, or both. And every single protocol has its own function, its own format, and its own rules. They can broadly be categorized into 4 different types. Communications protocols, so these enable 2 or more devices to communicate over 1 or more networks. Security protocols, so these secure the data, they give you authentication, integrity, and encryption. Routing protocols, so these are what allow routers to exchange routing tables and routing information and select the best path for packets to traverse through the network. And then service discovery, so these are used for detecting devices and services automatically over the network. Now, devices used agreed upon protocols to communicate. And these protocols could have one function, they could have more than one function. They could deal with addressing, so they identify the sender or the receiver. They could deal with reliability, so they could provide guaranteed delivery, or not, depending on the protocols you're using. They could implement some sort of flow control that allows data to flow through the network at an efficient rate, so nothing gets overwhelmed and everything works very nicely. Sequencing, so these are when segments are labeled so they can be put back together in the right sequence at the receiving end. Error detection, so this is how you determine if data has become corrupted during the transmission. And application interface, this is the process-to-process communications between your different network applications. Now, networks require many protocols. It says several. There are many, many protocols. And every single protocol has its own function and format. And here's just a couple of the protocols that we deal with. So HTTP is Hypertext Transfer Protocol, and that governs the way web servers and clients interact, and it defines the content and the format for web pages, stuff sent over the internet. TCP, Transmission Control Protocol, that manages individual conversations within a network. It provides guaranteed delivery, and it does so using flow control, ensuring that enough data is sent for optimum performance and efficiency. IP, that delivers messages globally from sender to receiver. There's a couple different versions of this that we're going to look at in a wee bit. And then Ethernet, so that's what's responsible for delivering messages from one NIC to another on the same network segment, the same local area network segment. And that brings us to protocol suites. So protocol suites, really all protocols have to be able to work with other protocols, right? A protocol suite is simply a group of interrelated protocols that works together to solve a problem. They can be viewed in terms of different layers, which we're going to look at shortly. Higher layers and lower layers. So in the upper layers and the higher layers, data is closer to the way we see it. And in the lower layers, it's responsible for moving the data and providing service to those upper layers. And when you look at the actual data, at some point it's all binary, right? So there's a couple different protocol suites that are out there that we use in industry, and not all of these are still in use. TCP/IP is the one we tend to use the most. So we've got protocols up at we've got our 4 layers, right? Our application, transport, internet, and network access. And with TCP/IP, we're dealing with HTTPS, DNS, DHCP, FTP, all up at the application layer. TCP or UDP down here at the transport layer, and your different versions of IPv4 and IPv6, and ICMP. That's ping, the protocol that lets ping operate. Version 4 and 6 down at the internet layer. And then down at the network access layer, that's where we've got Ethernet, ARP, and wireless LAN, right? It's also ISO, which we use the OSI model that comes from that a lot. Apple Talk, which is Apple proprietary stuff. I'm not sure how much of that is actually still in use with Apple, because I'm not an Apple guy. And Novell NetWare, which is ancient, really ancient. But the one we're going to look at the most is the TCP/IP model, and that's it's the most common one, and it's maintained by the IETF, the Internet Engineering Task Force, who I believe we talked about in the first lecture. Maybe it was the second lecture. I think we already talked about them. Maybe we didn't. Maybe I'm getting my courses confused. It's entirely possible. So TCP/IP protocols operate at the application, transport, and internet layers. And they're the most common network access layers on LANs and WANs. LANs and wireless LANs. So here's again an example here. I've got HTTP, so that's a web page, right? That's up at the application layer. At the transport layer, it's being sent with TCP, coupled with IP, and that's for your end-to-end addressing. And over the network, it's dealing with Ethernet. So TCP/IP is a protocol suite that's used by, well, it's used by the internet, right? It makes the internet work, and networks work, and there's a whole bunch of protocols in it. It's an open protocol suite, so that's partially why it's so popular. It's freely available to anybody, and any vendor can use this and design equipment to work within this, or software even to work within this. It uses standards, so it's a standards-based protocol suite. It's been endorsed and approved by various standard organizations within the industry to make sure that everything works together. So up at the application layer, up at the top there, that's where we have all kinds of things that we use every day, and you might not even know about it. DNS, so that's what maps domain names to IP addresses. So instead of having to remember the IP for Google's web server, you just type in google.ca and there you go, right? DHCP version 4 and 6, and Slack stateless auto address configuration, address auto configuration. I always get that one backwards. These are what dynamically give your device's IP addresses on the network, and we're going to look at these a little more in depth later on in the semester. Email protocols, you tend to deal with SMTP and IMAP. POP3 is pretty old. You don't really use it that much anymore. IMAP is for mobile. It supports mobile devices better, so that's why it's very popular. And SMTP is for communication between different email servers. For transferring files, we've got FTP, SFTP, and TFTP. You tend to use SFTP more often than not because it's encrypted. And in the web and web service category, we've got HTTP and HTTPS. And again, you tend to see HTTPS more commonly because, well, it's encrypted. Encryption's a good thing, right? Down at the transport layer, we see two. We see TCP and UDP, which I think we're going to get into a little bit more later, if not today, then in a later lecture. But TCP is a connection-oriented protocol, so it makes sure that the data is sent and received and retransmits anything that's lost or corrupted. And UDP is built for speed and efficiency, so it doesn't have mechanisms to deal with that. UDP just it doesn't care because it doesn't have a way to do that. And we're going to talk about those more in a later lecture. I'll tell you a funny joke when we do that. Down at the internet layer, we've got IP. So that's IPv4 and IPv6 and NAT. That's for translating internal addresses to external addresses. We're going to play around with NAT later. I think it's this semester. It might be next semester. ICMP version 4 and version 6. So that's the protocol that that ping functions on, right? It's the protocol behind ping. And ICMP v6 neighbor discovery. That's for IPv6. It's for discovering neighbors. It's kind of how DHCP works in IPv6. And then we've got a variety of routing protocols like OSPF, BGP, EIGRP, none of which we're touching on this semester. You're going to learn about OSPF in semester 3. And I think maybe a little bit in semester 2, but definitely semester 3. And then down at our network access, that's where we've got ARP, Address Resolution Protocol, and your data link protocols like Ethernet and wireless LAN. So here's an example of it all put together. We've got a web server encapsulated in sending a web page to the client. The client is then decapsulated, so that stream of bits is put back together and passes to the browser to display to the user. So we've got our data. Within there, we've got our, I guess, that's the inside of the packet, right? The inside of the packet's the data. That's encapsulated in a TCP segment. because we're using TCP, not UDP. And then that's encapsulated in an IP packet. Could be IPv4, it could be IPv6, it doesn't matter in this particular example. And that, again, is then encapsulated within an Ethernet frame. So the IP that has our layer 3 addressing, right, our IP addresses, our Ethernet frame that has what we call layer 2 addressing, or our MAC or hardware addresses. There's a variety of different standards and organizations we use because we like open standards, right? Open standards encourage interoperability, meaning that you can buy networking equipment from any vendor and integrate it into your network, and you know it's going to work together. You get competition because, well, if I'm producing routers and somebody else wants to come along and produce the routers that I'm making at a fraction of the cost and undercut me, they totally can, which drives down the price, and you end up getting better products out of it, right? It also makes me to say, okay, well, no, you know what? Maybe I do want to keep charging more, so I'm going to innovate my product a bit. I'm going to make it better somehow, or maybe I'll do something with the support. I'll offer better support options or something, right? So open standards are a good thing. They're all overseen by standards organizations, such as the ones depicted on the screen here, the IEEE, the IETF, the IANA, ICANN, the ITU, and TIA, and they are all vendor-neutral, non-profit organizations, and they're all established to develop and promote the concept of open standards, because working together is a good thing. There's a whole bunch of standards that that deal with how the internet works, and they're overseen by the Internet Society, or ISOC. So they promote the open development and the evolution of the internet, which is always changing, right? Always changing. And then we've got the IAB, the Internet Architecture Board. They're responsible for managing and developing internet standards. And then within there, we've got the kind of subsidiaries, the IETF. Sorry, I was moving around. Hopefully that wasn't too distracting. The Internet Engineering Task Force. So they develop and update and maintain your different internet and TCP/IP technologies. And the IRTF, the Internet Research Task Force. So they're focused on long-term research related to all these protocols. Looking at how things are going to change to support future networking trends, right? Look back, maybe not 10 years ago, but more like 15 to 20 years ago now. Mobile devices weren't really much of a thing, right? And now you can't imagine life without them. And that changed how we use the internet. So the IRTF would have had to have come up with new protocols to support this, which are really just new implementations of the old protocols. Everything, in some cases, is just a new implementation of something we used to do. We've also got a couple standards involved in the development and support for TCP/IP. The ICANN, the Internet Corporation for Assigned Names and Numbers, so they deal with IP allocation and managing domain names and other information like that. The IANA, the Internet Assigned Numbers Authority, so they oversee and manage IP address allocation, domain name management, and protocol identifiers for ICANN. So they're pretty handy. The IANA deals with things like port numbers, which we're going to look at later in the semester, domain names, and IP addresses. And then, of course, we have our electronic and communication standards. We've got the IEEE, the Institute of Electrical and Electronics Engineers, and I can honestly never remember what that one means. It's just the IEEE. They deal with creating standards for power, energy, healthcare, telecommunications, and networking. So they have a lot of standards. We're going to deal with a lot of their stuff. The EIA, the Electronics Industries Alliance, so they deal with standards relating to wiring, connectors, and even those 19-inch racks that we use for mounting network equipment. They're the ones who came up with a standardized unit, a rack unit that we use to measure equipment with. It's kind of cool. TIA, so they deal with communication in radio equipment, cell, VoIP, satellite, all that kind of stuff, right? And then the International Telecommunications Union, or ITU, and they define ITUT. Sorry, I sort of cut the acronym off because there was a lot there. They define standards for video compression, IPTV, internet TV, broadband communication like DSL, all kinds of useful stuff. Pause for some water. I'll continue. So now on to the different reference models that we're looking at, which I referenced earlier, mentioned earlier, the OSI model and the TCP/IP model. So we've already kind of talked about the TCP/IP model. We've got our 4 layers: our application, transport, internet, and network access layer. And here's where our different protocol suites, our protocols within the TCP/IP suite fit in. And this is how things are often used in networking, but the more split up model that academics tend to use a bit more is the OSI model. It's a 7-layer model. It breaks the top 3 down. Sorry, I was a little distracted. Top 3 down into application, presentation, and session. Makes up the application layer into the TCP/IP model. Transport layer stays the same. Internet layer becomes network, and network access gets split into data link and physical. We tend to refer to this a lot. You heard me mention layer 2 and layer 3 protocols earlier. The top layer is layer 7. Bottom layer is layer 1. And we're going to be looking at this extensively this semester. So it's useful, extremely useful, using a layered model, because you can have protocols that are designed to operate at specific layers, and they have to have the information, they have to work with the layers above and below, right? You get more competition because different products from different vendors can work together. It prevents technology or capability changes in one layer affecting other layers, and provides a common language to describe networking functions and capabilities. So it's a useful thing. And here's our layers here, right? So we've got our application layer that's up at layer 7. It's got our protocols for process-to-process communications. Next at layer 6 we have our presentation. So that provides representation for data transferred between your different application layer services. Layer 5, so we're working our way down, is session, and that gives you services, provides services to the presentation layer, and it manages the data exchange from the lower layers. The transport layer, that's where we're looking at services for segment transfer and reassembly from the data for the different communications. So this is where we're using TCP or UDP. The network layer, layer 3, right? So that's providing services to exchange the data over the network. That's where we get our end-to-end addressing, our IP addressing, version 4 or version 6, right? You'll commonly hear that referred to as IP addressing, or layer 3 addressing, or logical addressing. You might hear any of those 3 thrown in, and they mean the same thing. Data link layer, so that's describing methods for exchanging frames over common media. That's layer 2 addressing, or MAC addressing, right? Or even hardware addressing. You might hear any of those. And then down at the physical layer, so that's activating, maintaining, and deactivating the individual connection. And at that level, everything is some representation of binary. So here's our TCP IP model for reference. We already went over how it's simplified, and we're going to look at it again on the next slide. And there it is. So our top 3 layers in our OSI model are just the application layer. Our bottom 2 layers are simply the network access layer. Network becomes internet and vice versa. And yeah. Usually when we're talking about layers, we're talking about the OSI model here. So we're going to look at, I think next week, starting at the physical layer and work our way up. It's going to be a fun time. So with all that in mind, let's look at encapsulation and see how that works. So first, messages are segmented. So that's the process of breaking the messages into smaller units. And then they can then be interleaved on the same common media, which is called multiplexing, right? So we have multiple different messages on the same stream at the same time. Segmenting gives you increased speed and efficiency. So you can have a lot more data sent over the network without tying up the link the entire time. And you can only request segments that failed to reach the destination be retransmitted and not have to retransmit the whole stream. So it's a great thing. Now, of course, if we're using TCP, we're going to have sequencing. So this is numbering these segments before they're put onto the medium, so they can be reassembled at the destination. TCP does this, UDP does not, and that's why, well, UDP just has no mechanism for dealing with lost packets. This is one of the main things. Encapsulation is simply the process of the protocols adding their information to the data, and the data being broken down into smaller bits, right? I hate to use bits because it's a unit in there. So up at the top layers, we refer to data as simply data. It's a data stream, right? And then it becomes segments, and then packets, and then frames, and then bits. That's how it's referred to in the TCP IP suite, and that's what we're going to use throughout this curriculum. Encapsulation is a top-down process, so the level above does its process and then keeps passing it the information down to the next level, and it's repeated until it is sent out as some encoding of a bit stream. So we already looked at, we've got our data, right? It's encapsulated in a TCP segment, which is encapsulated in an IP packet, which is encapsulated again inside an Ethernet frame. De-encapsulation is simply the reverse, right? So it's received as a bit stream, and it gets passed back up the stack and converted back into a frame. Now the data link and network layers, layer 2 and layer 3 respectively, there's addressing that delivers our data from source to destination. At our network layer, we've got source and destination IP addresses. So this does not change throughout the entire transmission of the packet or life of the packet. Down at the data link layer, there's source and destination addresses. They're MAC addresses, right? And they do change as that frame is traverses the network from one device to another all the way through. So here's our layer 3 packet, our logical address, our IP address, right? 3 different names. So the source IP in this case is going to be this PC right here. The destination is going to be the server here. It's going to pass to router 1 and then router 2 and then end up at the server, and that's not going to change for the entire duration that packet is traversing the network. And there could be more routers in here too. IP addresses contain 2 parts, or consist of 2 parts. The network portion in IPv4 or in IPv6 we refer to that as the prefix. So that's the leftmost portion of the address, which indicates the which section of the network is unique to the network, and which section is available to hosts on the network. And then we've got the host portions. That's the remaining part of the address that's not specified by the network. It could be an interface ID if we're dealing with IPv6. So that's unique to every device on the same network, and this is the same for every device on that particular network. Sorry, I was moving my headset. When devices are on the same source and destination, or have the same, they're on the same network. The source and destination will have the same number in the network portion of the address. We're going to look at IP addressing more later in the semester. But there we go. We've got the first 3 octets are the same. In this particular case, we would need the subnet mask to know that that represents the network, so they are on the same network. There's our frame, and there's our source and destination IP header. Now, when devices are on the same Ethernet network, we look at the frame, the data link layer frame, right? Layer 2 frame, or Ethernet frame. And that has the actual MAC address of the destination NIC. Now, MAC addresses are physically embedded into NICs, and they're used locally. The source MAC address will match exactly the source hardware that sent that out, and the destination will be the same for the destination device that's receiving it. If the ultimate destination or actual destination isn't on the same LAN and it's remote, well, then a bunch of things happen, right? So when source and destination IPs in our header have a different network portion, it means they're on different networks. So then layer 3 will provide layer 2 with the local default gateway IP address, or the router, and that will be the destination MAC address that goes in the header. That packet will then go towards that router, who presumably knows what to do with that packet, or that frame, I should say. At the router, the frame is stripped off after it's examined. The router then looks at the source and destination IP addresses, looks inside its own routing table to determine where to send that, re-encapsulates the router with a new frame, or the packet with a new frame, with itself as the source, and the next hop on the journey as its destination, and sends it along its way. So the layer 2, the local addressing, this stuff here, that's going to change at every hop along our journey. But the layer 3, the network addresses, that's not going to change. So here we go. We've got the data link addressing. It's local, so it's going to have the same source and destination for each hop along the journey. So that's where it goes, right? Or it's not going to have the same. It's going to be different. The MAC address for the second hop, right? So this is just walking you through what I just said. So I'm going to skip ahead a bit. So it passes through the first router, repeats that process, right? Goes to the second router, repeats that process, goes to the web server. The web server strips off that frame, looks at the packet, realizes it's for him, right? It's for the server or her. I don't know. Could be, who knows what the server is. And the server then passes it up the stack where whatever has to be done with the packet. So throughout the entire life of the packet, the source and destination IP address don't change. But the source and destination in the frame, the Ethernet, the layer 2, that changes every single hop along the journey. Every single one. That's the important thing to take away from this. So what did we learn? We learned about protocols, right? The rules that dictate what happens in networking. They're protocols. There's different protocol suites, the OSI model and TCP/IP model. You're going to want to get very comfortable with those. We use open standards a lot because, well, they allow networking equipment to work with anyone else. There's two models that we tend to use for reference. The TCP/IP model, it's got 4 layers, and the OSI model, it has 7. With the OSI model, the bottom layer is layer 1, the top layer is layer 7. Encapsulation is just taking the data and breaking it down until it's a stream of bits that goes out with some sort of encoding on the network. And access is dealt with at layer 2 and layer 3, our network and data link layers, layer 2 being data link, layer 3 being network. So they give us our addressing. Layer 3 gives us IP, version 4 and version 6. Layer 2 gives us MAC. The layer 2 addressing is going to change in the frame at every hop along the journey, and the layer 3 is not going to. That's our summary. Hopefully that made sense. It's a lot quicker watching it as a video, isn't it? So take care, be safe. I hope you have a great week, and I hope you had an awesome long weekend. Next week we will meet in the virtual classroom as normally scheduled. And this Friday you're going to have the full 2 hours to work on some labs, so that's pretty awesome. We're going to be caught up and hopefully good to go. Take care, be safe, have a great week. Bye for now.